So, in this lecture I am going to basically do a few problems, but as I do some of these problems I will try and point out to you some interesting facets of the results. So, to begin with, let me quickly point out that the basic and the fundamental equation that we are going to again and again use is this wave equation. Eta here is the displacement. In the lecture today we are going to confine ourselves to longitudinal waves, and the phase velocity here can be easily identified from this equation. Square root of b by rho, b is the bulk modulus and rho is the density of the medium. And when we specialize to the case of sound waves in air, as we had seen before, this formula for the speed of sound becomes gamma p by rho, where p is the pressure, gamma is the ratio of specific heat. This wave equation that we have obtained is also valid for longitudinal waves in a solid. Typically, the additional complication in a solid is that when you, let us say, try and excite a wave in a solid, you are actually stressing the solid, in the sense that you have applied some pressure, maybe you hit it with a hammer for example, and that is how you created a propagating wave inside a solid. So, the situation is a lot more complicated in general. So, if you had a huge solid body and if such waves are travelling, so it is going to create pressure variations inside the solid. There is going to be dilation of the material in some places, there is going to be a compression of the material in some other places. What happens is that if you try to stress, let us say, in one particular direction, it is going to strain in directions that are perpendicular to it. So, which means that you have to worry about stresses in different directions and the resultant strains in all other directions. If I confine myself to a thin object like this, something like a long rod, where one of the dimensions is much smaller than the others. In such a case, you could ignore these effects of strains being produced in perpendicular directions. In that case, it so happens that you could use the same wave equation as the governing equation for propagation of longitudinal waves in solid. Hence, we can still be fine with dou eta by dou t square is proportional to dou square eta by dou x square. So, here the proportionality constant will be bulk modulus by rho, but bulk modulus should be replaced by Young's modulus here by rho. So, Young's modulus is of course stress divided by strain. So, that is the correct elastic property that should be used in the case of a solid, and here it must be used more correctly in the case of a solid which are in the form of a rod or something similar, where one of the dimensions is much smaller than the others. So, in this case, of course, once we have made this modification, immediately we can write out the velocity of sound in a solid as c square is y by rho. So, once we sort of understand this generalization, before we start doing some of these problems, let us look at the standard results. So, we know that the solution for the wave equation is eta, which is the displacement as a function of position and time. So, it is either a sine or a cosine function, you can choose any of that until it is a function of k x minus omega t finally. and the solution can also be written in terms of pressure variations. So, here the solution is written in terms of pressure variations indicated by P, which is a function of both position x and time t. And note crucially that between displacement and pressure there is always a phase lag of pi by 2. And we also saw that we can define intensity of these waves. So, we went through this whole lecture on deriving the intensity as the total energy which is transferred per unit area. So, when you go through all the derivation, finally you get this result that intensity is the expression that is given here. Importantly, you notice that intensity depends linearly on rho and on C. And the first of these expressions that I have written here is intensity, which is in terms of the maximum amplitude. So, it is proportional to the square of the maximum amplitude. But as I explained in the last lecture, the intensity can also be written in terms of pressure variations or velocity variations or acceleration variations. So, here I have written another of those expressions, which is in terms of pressure variations. So, the maximum amplitude of pressure, which is P max, and then we went ahead and in order to standardize the intensity, we assume that there is a reference intensity level I 0, which is identified with the just about audible voice for a human being, and that is I 0, and any other intensity is measured as a ratio with respect to I 0. So, the intensity level is measured in units of Bell, or Bell is a very large unit, hence often the standard unit that is used is decibel. So, that is given by this formula here. L is 10 times the log of I by I 0, where I is the intensity of our waveform, I 0 is the reference intensity. So, the question is as follows: the velocity of sound in air is given, it is 330 meters per second, and density of air is 1.29 kilogram per meter cube. The question is, what is the acoustic pressure for painful sound of intensity, which is about 10 watt per meter square. So, the sound intensity is 10 watt per meter square. What is the corresponding acoustic pressure? So, we need to find the maximum amplitude of pressure variations for this kind of intensity of sound. So, let us collect two of the formulas that we know. So, one is I is equal to half rho omega square C, C is the velocity of sound, y max square. So, this form relates intensity to the maximum of displacement, which is y max, and we also know that P max is related to y max B k into y max. So, you will notice one thing, that I have been using this eta and y interchangeably. For me, both are displacements, both are longitudinal displacements. If you want to fix your ideas, you can think of them as longitudinal displacements of a parcel of gas, for example. So, most of the time I seem to have used eta in the equation of motion, in the wave equation, and I have quoted the solution here in terms of eta, but many times when I was doing problems I have used y. So, you should keep in mind that both eta and y represent displacement for us, and y max or eta max is the amplitude. Problem is sort of simple. All I need to do is to substitute, eliminate y max, because I do not know y max. What I know is intensity of sound, and what I want to find out is P max. So, using these two equations I can simply eliminate y max and directly relate intensity to P max. So, this for example will give me that y max is equal to P max divided by B is the bulk modulus and K. So, if I substitute this in this equation, I will get the following, and from this relation I can extract what is P max. So, that would be 2 I into B square K square divided by rho omega square C, and of course, I need to take a whole square root here. But you will notice that we do not have all the information that is needed for this formula. For instance, we are not told what is the bulk modulus and K, the wave number. So, we do not have all this, but clearly there has to be a way out. The point is to recognize that B by rho is equal to C square. Hence, we can eliminate B using this relation, and also that omega by K is equal to C. So, if I substitute all this in this equation, you will notice that. So, this tells me that to calculate P max I need to know intensity, velocity of sound and the density. That is exactly the information that we have. So, we just need to put in all those numbers, and that will be 2 multiplied by intensity, which is 10 watt per meter square, and C is given as 330 multiplied by 1.29, which is the density, and this you can use your calculator to calculate. So, notice that this one will give you the pressure in pascals, and I have converted it into atmospheres, and the reason is that the standard atmospheric pressure is of the order of 10 power minus 6 atmospheres. So, clearly the value that we have obtained for a painful sound of intensity 10 watt per meter square is 100 times larger than the standard atmospheric pressure. So, which means that if you are exposed to such a sound whose intensity is like 10 watts per meter square, we are talking of 100 times more pressure on your, let us say, the eardrum than what is imparted by the standard atmospheric pressure. The next problem is as follows. So, there is sound at an intensity level of about 10 watts per meter square. The question is, what is the displacement amplitude of air? So, which means find the maximum of the displacement of your air parcels when the sound is of about 500 hertz frequency. So, y max will be 2 I divided by rho omega square C square root, and now we just need to put in the numbers, keeping in mind that omega is 2 pi times the frequency, where the frequency is given as 500 hertz. So, this will be 2 multiplied by intensity, which is 10, divided by rho. Of course, we know the value of rho, which is about 1.22 multiplied by. So, this is 2 pi times the frequency whole square 2 pi times frequency is 500 whole square multiplied by c. C is of course the velocity of sound, which I will take as 330. So, this is the displacement amplitude for an intensity level of 10 watt per meter square. Now, you should compare with what we had done before. Earlier on, towards the end of the last module, we said that in quiet room or room with conversations between just one or two people, we saw that the displacement amplitude y max was of the order of 10 power minus 9 meters. So, clearly in this case the amplitudes are 10 power 4 times larger compared to the amplitudes of sound in a quiet room. We can also calculate what would be the sound level in decibels, and that would be 10 times log of I by I 0 log taken in with respect to base 10. So, this would be 10 times log of 10 divided by 10 power minus 12. So, this gives us 10 log 10 power 13. So, that is 130 decibels, which is very high. Continuous exposure to such kind of sound levels can be quite damaging to the ears. The third problem, we have two sound waves, one of them a progressive wave in water and other in air, and we are told that both have the same intensities. So, ideally this I w and I a that I have written down are actually equal to one another. So, the question is find the ratio of their pressure amplitudes or the maximum of the pressure displacements. So, I had already introduced to you this formula which relates the pressure amplitude or amplitude of pressure variations to the intensity I. So, we are going to use this one, and from here it is a very straightforward exercise. So, P max is square root of 2 I c into rho. C is of course the speed of sound. So, now we have two media, water and air. So, we just need to consider both of them. So, let me say that P W. So, the W tells you that it is water, maybe I will put it in brackets. So, this is 2 I W to indicate that intensity of sound in water, C velocity of sound in water, and rho density of water. So, we just need to divide one by the other to get the ratio. The ratio is equal to C W rho W divided by C A rho A. So, the information that I need is the speed of sound in water, density of water, speed of sound in air, and density of air. So, speed of sound in water is roughly 1481 meters per second multiplied by the density of water, which is about 1000 kg per meter cube, divided by speed of sound in air, which is 330 or approximately 330 or 332, multiplied by density of air, which is 1.22, and we need to take the square root. So, if you do this, we will get something like 60.34. The amplitude of pressure variations in water when say a sound wave travels through it is 60 times larger than the corresponding pressure variations in air. for a fixed intensity of sound waves. So, the last problem I am not going to do in full, it is a version of the problem that we had done before. So, it is the same question that keeps occurring again and again. Suppose sound waves travel from one medium to another medium, what happens? So, you have an incoming waveform and an reflected waveform. So, this is reflected, this is of course the incident wave, and then there is a transmitted wave in the second medium. So, here, so you could assume that x equal to 0 is the point where the interface between two media is, and the first medium corresponds to acoustic impedance Z1, which will be rho 1 C1, and the media on the right hand side corresponds to acoustic impedance of Z2, which is rho 2 times C2. So, rho 2 is the density and C2 is the velocity of sound in that medium. So, the question is standard, like if I had an incoming wave, what fraction of it is reflected back into the same medium, what fraction of it is transmitted into the second medium. The way to do it is precisely the same as what we had done with the transverse waves. The only difference and the crucial difference comes in the treatment of the boundary conditions. So, here we will have two boundary conditions like we had in that case there. So, one is that the particle velocity, which is eta dot, has to be continuous at x equal to 0, and secondly the acoustic pressure given by P, that this has to be continuous at the interface between the two boundaries. Clearly, you can see that the boundary conditions are physically motivated. So, you do not want particle velocities to be suddenly changing across the boundary, does not make physical sense, it does not happen. Neither does pressure suddenly change in the absence of any other external mechanism to make it happen. Hence, we want that both these quantities be continuous at x equal to 0, which is the interface between the two media. So, this is one set of relations that you will get from implementing these boundary conditions. So, now putting all these together, we will have the following equation, which is, so now rest of the exercise is to simply write these equations in terms of Z1 and Z2. So, eliminate everything else, so that your final result for the ratio of eta t by eta I and p t by p I comes out in terms of Z1 and Z2. So, I will leave it as an exercise for you to do that. So, that eta t by eta I should finally turn out to be 2 Z1 by Z1 plus Z2. P r by P I will be Z2 minus Z1 by Z1 plus Z2, and you can also calculate P t by P I, which will be 2 Z2 by Z1 plus Z2. So, again you will come back to the familiar result that the intensities of waves that are transmitted and the intensities of the waves that are reflected, the sum of these is equal to the intensity of the incoming wave. So, it is just a restatement of the principle of energy conservation. It is a simple question of manipulating these three equations to obtain these results, And further, I would urge you to rewrite all these in terms of the intensities, and you will see that you can finally make a statement that the incoming intensity has been distributed between the transmitted intensity and the reflected intensity.